Continuing where we left off in the last video with chapter 11, we started talking in section 10.2, the last part of section 10.2, about amphoteric or amphiprotic substances. So those are acids or bases which can kind of go both ways, all right? So they can, in certain cases, they can act as an acid, and in other cases, they can act as a base, depending on what they're reacting with, all right? So, for example, water, when it reacts with HCl, then it acts as a base. However, when it reacts with ammonia, it acts as a proton donor or an acid. Okay. Similarly, the bicarbonate ion. Okay. As you can see here, if it grabs a proton, okay, that means it's acting as a base, and when it grabs that proton, it becomes H2CO3. Okay. When it gives up its proton, then it's acting as an acid and it becomes CO3 2 minus, the carbonate ion. All right, so the bicarbonate ion can act as a base, becoming carbonic acid, or it can act as an acid and become the carbonate ion. Similarly, water, when it grabs a proton, becomes the hydronium ion. All right, acts as a base. Or if it gives up one of its proton, then it becomes OH minus, the hydroxide ion. All right, okay. So it will donate its proton when it is reacting with a stronger base. All right, so when water is reacting with ammonia, which is a stronger base compared to water, then it becomes an acid. When it reacts with a stronger acid, then of course it's acting as a base. Okay. So when you're writing conjugate acid base pairs, remember they have to be related. All right. So identify the one that is losing its H plus. All right. So the acid part will have one H plus more than the base part. All right. Okay. But they have to be related. All right. HCl and Cl minus. All right. So what they have in common is that anion. Okay. So the acid is HCl, the conjugate base is Cl minus, all right? So they have the Cl minus in common. The acid has one extra H plus. All right, so identify conjugate acid base pairs here in this reaction. Here you have HNO3, and then on the other side you have NO3 minus. So that means the proton has come off, it's acting as an acid. That proton has joined up with ammonia, so that ammonia is acting as a base, and so therefore its conjugate acid is NH4 plus. All right, so this is HNO3, the acid, conjugate base is NO3 minus. Okay, so as you can see, the acid and its conjugate base are related in terms of this anion. Okay, the acid has one H plus more than its conjugate base. In this case, this is the base, ammonia. Its acid has got one H plus more than the ammonia. Okay. Section 11.3 talks about acid and base strengths. Okay, and we already learned this from solutions, that if something breaks up in water 100%, it's deemed to be strong because all that is left in water is just ions. Now, hydrogen fluoride is not breaking up 100% in water. All right, you have some H3O plus and some F minus, but most of the hydrogen fluoride remains intact as molecules, all right? So therefore, hydrogen fluoride is a weak acid. Among the halogen acids, this is the only one that is the weak acid, because HCl, HBr, and HI are very strong acids. They break up 100% in water. So a strong acid will break up, ionize 100% in water, right? So as you can see here, HCl completely break up and form ions, H3O plus, Cl minus. The single arrow indicates that this reaction goes to completion. A weak acid like carbonic acid or HF, on the other hand, you see the double arrow indicating it's a weak dissociation, and it forms a few ions, all right? So one of the H pluses comes off and joins up with the H2O, becoming H3O plus. This is what makes water acidic. And then what's left is the HCO3 minus, okay? Now, acids like carbonic acid are called as diprotic because they have potentially 2 protons that can come off, all right? However, it's a stepwise process. In the first step, only 1 comes off, and then if this further ionizes, then the second proton can also come off. So a strong acid completely breaks up 100% in water, right? So it's always going to be the H3O plus, and the A minus is the generic form of the anion, all right? Okay. So as you can see here, all you see in water are these. This is HI, it's similar to HCl, and all you will see is as soon as you dissolve the HI into the water, all you'll see in water is just this. There is no longer any of the HI present. A weak acid like HF, on the other hand, you can see that there's a little bit of H3O plus and F minus, but most of it is HF, the unbroken acid, okay? H2CO3 carbonic acid is very similar. You'll see a few, maybe 1 or 2 of the H3O plus and HCO3 minus, but most of the unbroken acid would be carbonic acid in water, H2CO3. So table 11.3 is showing you the listing of strong acids as well as weak acids and their strengths, all right? So if you follow the red arrow as the arrow goes up, it shows how strong the acids are. At the top of the list is HI. So among all of the acids, HI is the strongest acid, all right? So among the halogen acids, as you go down the group, the strength of the acid is increasing. That's why HI is the strongest acid, HBr is the next stronger acid, and then you have HClO4, the perchloric acid, followed by HCl, all right? Below HCl is H2SO4, and below that is HNO3, and then you have H3O plus, the hydronium ion, all right? So these are all the strong acids, which means that they break up in water 100%, okay? Now, their corresponding conjugate base, on the other hand, is weak, all right? So if you follow the blue arrow, you will see that the base strength is increasing in the opposite direction, all right? So the strongest acid has the weakest conjugate base, okay? The weakest acid, which is water, has the strongest conjugate base, which is OH minus, all right? So they are in opposite direction. Now, among the weak acids, you can see you have the bisulfate or the hydrogen sulfate ion, which is weak, followed by phosphoric acid. So this list is useful as we will see a little bit later on, okay? All right, so if you compare a strong acid and a weak acid like acetic acid, strong acid like HCl, both the same strength. They're both 1 molar solutions. And you see that in HCl, all you see is ions, the hydronium ion and the Cl minus. Whereas in acetic acid, you see like a couple of H3O plus and the C2H3O2 minus, the anion part. But most of what you see in solution is the unbroken acid, all right? So the acid doesn't dissociate much in water, which means it's weak. All right, this is another slide comparing strong and weak acids, and we have already looked at this before. You can see that it's only ions for a strong acid in water, whereas for a weak acid, it's some ions, but mostly molecules. All right, we talked about diprotic acid. Di means two, protic means protons, all right? So H2CO3, H2SO4, those are called as diprotic acids because instead of just one H, you have the two H's in the formula, all right? H3PO4 would therefore be called triprotic because it has three H's that precedes the anion part, okay? So here H2CO3 can dissociate in the first step, forming H3O plus and HCO3 minus, all right? In the second step, the HCO3 minus can further dissociate and form H3O plus and CO3 2 minus, all right? The bicarbonate ion can then form the carbonate ion, okay? Now this first reaction where one of the H plus comes off, forming the bicarbonate ion, that is more dominant compared to the second reaction. The second reaction doesn't occur to the same extent as the first reaction, all right? So this is the case for most diprotic and triprotic acid. The first proton will come off rather easily, but then the second and subsequent protons will not come off that easily, okay? That means the acid strength gets weaker and weaker as each proton comes off. Okay. So you have very strong acids like sulfuric acids, all right, H2SO4. Basically goes to completion, single arrow, you get H3O plus and HSO4 minus. But HSO4 minus, the bisulfate ion or the hydrogen sulfate ion, is rather weak, all right? So that second reaction, you can see the double arrow indicating that unlike that first proton that came off and went to 100% completion, the second proton comes off to a certain extent, but it's less than 100%, all right? So that second reaction where the sulfate ion SO4 2 minus forms is much, much less compared to the formation of the bisulfate ion. Strong bases are group 1A and 2A hydroxides, all right? So any of the group 1 or group 2A hydroxides are considered to be strong bases, all right? So if there is a base which is not a hydroxide of group 1 or group 2, then they are weak, all right? So here you see potassium hydroxide breaking up into water into K plus and OH minus, again 100% dissociation. So most of the cleaners, etc., are bases. Weak bases like ammonia will dissociate in water. You see the double arrow showing that a little bit of the hydroxide and the ammonium ion forms, but very little. Okay. So here's a listing of the strong bases on the left side of this chart, and as you can see, they are all the hydroxides of group 1 and group 2A. Group 1A, of course, is very soluble. All right, we'll have to stop here.